This is the IBM Code Pattern on audio classification. In this code pattern, we will walk you through setting up a cloud object storage, uploading your training data on the cloud object storage, and training an audio classifier, and finally performing inference on Jupyter notebooks. This model uses audio embeddings as an input as opposed to raw audio. And embeddings, for those of you who are not familiar with it, are essentially an array of numbers or a vector of numbers. And in this case, the embedding length is 128 so for every second of audio. So we take 10-second audio clips or 10 vectors of length 128 each and feed it through a deep neural network. And at the end of the neural network, it outputs probabilities for different classes of audios that we have. This model is trained on the Google audio set, which consists of 527 classes of sound, ranging from music and speech to natural sounds like lightning and thunder and automobiles and pretty much anything you can think of. Um, Luckily for us, the audio set already pre-processes all the audio into embeddings, so we are just gonna pick off from having an audio embedding and then using those embeddings to build a classifier. Though the embeddings themselves do not convey much meaning as they are just a vector of numbers, they prove quite useful in tasks such as clustering or in our case classification. The first couple of steps that are prerequisites for this code pattern are setting up a cloud object storage and setting up a Watson machine learning service. The cloud object storage is where we are going to host the training files as well as the evaluation files. It's also the place where the Watson machine learning service is going to upload our model and the weights, and the machine learning service is the core service that trains our model. And if you go through these steps, you should be able to see both your service as well as the cloud object storage in your dashboard. And the service contains the service credentials, which we will be using in a step uh, later. And the cloud object storage should contain two directories as we've built it in the README. The training audio set classifier contains the files. So these are the training embeddings as well as evaluation embeddings. And the result directory contains whatever the code is generating, such as logs and models and weights and etc. Once this has been set up, you should be able to pull the repository, and um, that should look like this. And before you run the training, make sure that you key in your access key ID and secret access key that you generated from the cloud object from the IBM Cloud Service. I've already done that in another directory, and we should be able to train our model now. So, as mentioned in the README, you should be just doing this. So this is going to submit a job to the IBM Cloud. Okay, so if your job has been successfully queued, you should be seeing something like this, saying that this is your training ID basically, and you can also check the progress of it using this command. As you can see, our job is currently in the pending state, but it would move to processing and completed once it's done. Um, Once the model is trained, you should be able to see yeah, the results in the results directory. So right now it's just queued, so it might take a while, but then ideally you should be able to see your models with the same training ID. Just given the training ID and you should see the model files. For now, we would probably want to take one of the earlier models that I've trained. As you can see here, it should create files like this. The file we are looking for. So it creates a checkpoint after every 10,000 iterations. That is the default frequency. You could always dig into the code and change that. Um, the file we're looking for is the final weights at the end of the checkpoint. Make sure to download that file, and we'll be using that in the next step when we perform inference. Right. So for the inference, we'll be using Watson Studio. So this is a really convenient platform to host Jupyter notebooks. Before we go and into the notebook, make sure that, as mentioned in the README, you're linking your cloud object storage and you're uploading the final weights file that I've just mentioned. And you should be able to see these files here, or you can upload it through the UI just here, and then you can just upload the file here. So that's pretty straightforward. Once you have the files in the system, you can head over to the notebook that I've linked. So this is just a wrapper function for um, fetching the objects from the cloud object storage to memory. Um, so this code has been generated by the system. You need not worry about this code. All you have to do is just go to data and essentially click the file that you want to insert right now. Let's say the evaluation file, and then just click on insert credentials. So this already pre-fills all the required credentials for you. Just gonna go ahead and load all of them. And similarly, we can also load CSV files directly as a pandas data frame. For that purpose, you just go to the CSV file here, and then when you click on insert to code, you should be seeing an option that says insert pandas data frame. This makes it really convenient because, as you can see, all my data is already inserted into df data 1 and df data 2, and it's convenient. Now we load the data into NumPy arrays. So X is the embeddings and Y is the labels. This is evaluation data, so our network has not yet seen this data. So for all practical purposes, it does not know what Y is. It's just we are using Y to measure accuracy, or if you wanted some other metrics, but this is unseen data, right, basically for the network. And here is just a code to rebuild the model. This ensures that you build the model from scratch every time and avoid any versioning issues. And this is the weights file that we trained on the cloud. And we can just load that right now. So at this point, we have trained our classifier, downloaded the weights, and then uploaded the weights here into the model, and it's ready to perform inference. So let's just try out a random video, random sample. So we have, I believe, 20,000 random snippets in the evaluation data set. So let's just pick a random number 350 and perform inference on that. So so as you can see, this audio belonged to this particular video from the YouTube data, and our model predicted bagpipes, wind instrument, music, which is pretty decent. And we can just try out another video. Uh, so this model predicts cappella, vocal music, and singing, which is pretty cool. We can also build a simple application. Let's say you have a database of a lot of videos or audios, and then you converted them into embeddings. It would be neat to query a video or audio based on the actual raw audio rather than metadata. So what we could do is say, let's say we're gonna predict on the entire data set, and then we're just gonna queue for a particular query. So right now we, the model is going to predict for the entire batch, and once we're done with the prediction, we can hopefully search our database for a particular query. Like let's say you want audios of car or audios of guitar or piano or something like that. We have 20,000 embeddings, and so it's probably going to take a couple of minutes to perform inference. While we wait for the inference to be performed, for those of you who are interested in the math behind this model and the full architecture, the paper has been linked in the README. Feel free to explore as you wish. The authors have also open sourced the code. Right, so the inference is now performed. We've written a simple uh, wrapper function to basically queue the database of all the predictions for a particular query. Let's see. Let's say now that you have performed inference on your entire data set, you want audios or videos of car. Um, and basically, at this point, you don't have the data set labeled by humans, but you just have raw audio or video files. So let's see if our classifier the can query our entire database for this particular keyword. So based on probabilities, the we have the following videos. I'm sure we have more, but then these are probably I've written the code to just display I think the top 10 or the top 20, and basically you can just head over to any of these links and you'd probably find a car.
What's up, guys? I'm Jeff from Brave and Audio. This is the new Brave and Ready Solo.
Again, remember that at this point we had no information other than just the raw embeddings. So there was no label that said that this is a car or that video contains a car. It's just the actual embeddings generated from the audio files or the video files in this case. So it's pretty impressive that if you have a completely unlabeled database, uh, the model is able to retrieve results with pretty fair accuracy. Let's go and try something else, maybe a piano or a guitar. And this is all in real time, so
pretty much describe the basics of ska guitar. Let's get started. So we're going to talk about the basic ska rhythm right now. We're in the key of A and E for our chord progression.
It's pretty good. Maybe we can just check out another result. Yep, that's definitely a guitar. So that basically concludes the content on this code pattern. Uh, be sure to check out all the other interesting code patterns that have been linked at the end. Maybe you'd be inspired to create one of your own. And